Hello, everybody, and welcome to our last session, the last unit that we're going to be teaching all year. This unit is about velocity acceleration and particle motion, really. This is a particle motion that's not just in one direction. It's particle motion that's going to be in two directions, both an X and a Y. And this kind of topic actually extends itself to three-dimensional, where we're going to have particle motion within a three-dimensional field. That would be when our vector turns into x of t, y of t, and z of t at the same time. So going back to, this is a little bit of 9.6 as well, which if you remember, this is what we skipped over. We do have our position vector, which again, in two dimensions, our position vector is going to be x of t, y of t. Now that position, yes?
Are we supposed to be seeing the notes? Because we're not seeing that screen.
You are not seeing the note screen?
No, just your calculator screen.
Okay. How about now?
Much better.
Okay, there you go. So we have our position vector, which is going to be based off of x of t and y of t, which if they're x of t and y of t, then when we take our velocity vector, which our velocity is our derivative of position, so x prime of t, y prime of t, or you could see it as dx dt, dy dt. And if you view it in parametric form, it really kind of like merges the two ideas between vectors and parametric equations at the same time. And then we can go one step further and put all of this in a matrix, and you get all of the beautiful mathematics combined. So, but you'll be doing some of that next year. So speed, this is the one thing that I know there's some questions in the group chat about. Speed is going to be the magnitude of, actually, I believe that should just, or the magnitude of velocity. So that is square root of x prime squared plus y prime squared, which if you consider that we might have seen an equation that looked like that before, that would be really our same thing as our arc length formula. So the arc length actually models what goes on with the speed. Now, where this is important comes down to in multivariable, one of the things that you do is you have distance as your arc length parameter, or sorry, your distance as your parameter. If you use that distance as a parameter, a lot of different cool things happen, which not the nature of the course right now, but there's a strong connection there. And then acceleration is going to be our second derivative. So as far as calculus-wise, this isn't really that bad because it's just going to be taking some basic functions, finding first and second derivative, and then putting them in a vector and parametric form. So, with that said, let's take a look at problem number one. We have a particle that follows a path defined by a position vector. We have our position vector here. One of the things that I like to do with my position vector is I like to go ahead and sketch out what that path is going to be. So if I set my parameter, it doesn't really matter if x is e to the negative t or y is e to the t. Let's just go ahead and do something different and set our parameter as y equals e to the t. So then, since x equals e to the negative t, we could rewrite that as e to the t to the negative first power. So that's y to the negative first. So our relationship is x equals 1 over y, or y is going to equal 1 over x. Now, what's going to happen is we do have a limited domain based off of the parameter that we set. It wouldn't have mattered if we set the parameter x or the parameter y, but our domain doesn't matter what we plug in for t. So if t is a member of the set of real numbers, then y is always going to be greater than 0 based off of that. So what I'm going to be doing is I'm going to be graphing this y equals 1 over x, and I will graph this y over 1 over x only where y is positive. So some specific points that we have, 1, 1, 1/2, 2, we could say 1/3, 3, which is about there. We have 2, 1/2, 3, 1/3, which is about here. So here is going to be my curve. Okay, and now I need to, there's a path of the particle. What direction is the particle going? I really should not include arrows on both sides of this. Let's establish what happens at t equals 0. Then we have r of t is going to be e to the negative 0, which is really just 1, 1. So this point right here is t0, t equaling 1, r of 1. So I should have said that one was r0. R of 1 ends up being e to the negative first. So 1 over e, comma, e. And 1 over e, comma, e is going to be, that's 0.368, I believe. And then 2.718. So that would be right about here. So this is going to be T1, which establishes that the path of this particle is moving in that direction. So in a different color, what I'm going to do is I'm going to sketch the velocity and acceleration vectors at the given time. So I'm looking at t equals 0, our velocity vector. So our velocity vector, I really should just write it as r prime.
That whole part was cut out. That whole part was cut out, Mr. Beck.
Okay, thank you.
What you said.
What was the last thing you heard?
You started with
said, like,
velocity and then,
It cut out.
yeah.
Okay. So our velocity vector is going to be written as r prime of t. R prime of t is going to be e to the negative e to the negative t, comma, e to the t. And we want to know what r prime of 1 is, or r prime of 0 is then. R prime of 0 is going to be negative 1, comma, 1. So what I'm going to do is from my position at t naught, I am going to go horizontally negative 1, vertically 1. And we have this vector right here, which is our velocity vector. That velocity vector should reinforce exactly what we said before, that the direction of the particle, it's moving really like towards the positive y-axis. And then we have acceleration vectors. So this is our velocity vector. Our acceleration vector is going to be our double prime of 0. Let's start off with our double prime of t. Our double prime of t is going to be, once again, positive e to the negative t, and then e to the t. And that means our double prime of 0 is going to be 1, comma 1. I have this bad habit of not having those angled brackets. So where this is my r prime, our double prime is going to be right here. So this is our double prime of 0. So one of the things that you'll note on here is that r prime will show the direction, and then r double prime will show kind of that acceleration, that pull. And that pull towards the first quadrant really is the reason why our graph actually, our path of the particle acts in the way that we do. So the nice thing about working with velocity and acceleration vectors is they really help establish why the path is moving in the way that it is. Now, what is the speed? Speed is going to equal, if we look back up here, speed is the magnitude of the velocity vector. So speed is going to be the square root of -1 squared plus -1 squared. Oops, that one's a positive 1. So -1 squared plus +1 squared. And where I'm getting that speed is going to be the magnitude of this vector right here. So that speed is the square root of 2. Which, by the way, if you notice, is the length of this velocity vector. So deep connection there.
Can you repeat that, Mr. Beck?
Yes, so the length of the velocity vector equals the speed. All right. So on to problem B. So with this one, it's actually going to be a lot easier to immediately say that y is going to be our parameter of t, which means that x is going to equal 1 minus y squared. since x equals 1 minus y squared, taking a look at that, what is the path of the particle? This is a parabola. It's a parabola that opens to the left and is shifted right 1. Not fully sure how much of this you did last year. And once again, I have
Wait,
that
Mr.
happen.
Beck.
Yeah.
Why is it a parabola? Isn't it just a semicircle?
1 minus y squared.
Yeah, because when you set it equal to, when you do y in terms of x, it's square root of 1 minus x.
Plus or minus.
It should be plus or minus. Right here is,
Oh,
this
yeah.
is
Yeah.
the negative square root of 1 minus x, and then up here will be the positive square root. Now,
Oh, yeah.
not a bad thing to look at in general, just because we do want to understand what the, I keep putting that arrow on there. I don't want to. I do need to understand what the domain of this actual function is. If I establish that time is any real number, then by establishing that time is any real number, then can the y value be both positive and negative? The answer is yes. Can the x value be both positive and negative? And that ends up being the result of that, that time. So we should have everything that's possible, and we should have both halves of the parabola. So we want to know what's going on at different times. So kind of like what I did before, time 0 is going to be r of 0, and r of 0 is 1 comma 0. So this point right here is t0. Time 1, that would be r of 1, and r of 1 is going to be 0 comma 1. So if we look at 0 comma 1, this point right here is t1, which establishes that the parabola should be moving, or the particle should be moving along this parabolic path in this direction. So with that said, now that I have my time 1, the point that I'm really going to be emphasizing is going to be this point right here. So if this is time 1, let's go ahead and find r prime of 1. Let's start off with r prime of t. R prime of t is going to be negative 2t comma 1, which gives us r prime of 1, since that's the time that I care about. R prime of 1 is negative 2 comma 1. So let's go ahead and draw that in. Horizontally negative 2, vertically 1. This vector represents r prime of 1. Now, eventually, we're going to have to find the speed of this. To find the speed of this right away, we can either say speed is going to be the square root of negative 2 squared plus 1 squared, which is the square root of 5. If you notice, once again, the length of this vector is square root of 5. So that's our speed. And finally, the last thing that we need to do with this problem is we need to come up with the acceleration vector. So our acceleration vector is going to be r double prime of t. R double prime of t is just negative 2 comma 0, no matter what. So that negative 2 comma 0 is going to be this vector right here. This is r double prime of 1. So, and because the pole is purely in the negative x direction, that's why the parabola is moving faster and faster in that negative x direction. So, any general questions about either one of these two problems? Being able to draw a particle. So do you know how to draw the path of particles following? Do you know how to find the acceleration and velocity vectors? And then do you know how to find the speed of those? Yes, okay. Second portion of this is going to be displacement and total distance. So basically we did a lot of work involving integrals or derivatives. And that derivative is going to be the first derivative, which gives us both speed and velocity. Second derivative is going to give us the acceleration. Then we can go back and say, what is the displacement and the total distance of this vector path? So if we have a velocity vector defined in this way, which is how we defined it before, the displacement is going to be the integral of that velocity vector. So basically, everything that we did in single dimensional calculus or single variable calculus, this actually is going to work as well. That we want to know what is our horizontal displacement, what is our vertical displacement, which should give us something related to the position function. And that position function we can write as, I believe these are supposed to be brackets, not parentheses. So, oh, actually, those are supposed to be parentheses. So our position is going to be, in order to find our position at time B, we're going to take our known position at time A and then add what we always called the displacement before. So we're going to take our initial position and then add the displacement to it. And then the total distance, which if you notice, that's what I've been kind of referencing this entire time. The integral of the magnitude is going to be the integral of the integral of the magnitude is distance. Sorry, I'm getting distracted by the noise in the background. Hopefully it's not too loud for you guys. So now, if you think about how we did this in single variable calculus, we said the total distance in single variable total distance is going to be the integral of the absolute value of velocity, dt. So when that was from A to B, this is really just a natural extension that now we're saying our velocity is a vector. We need to find the speed. So kind of cool. All right. So a car is traveling down a road starting at time t equals 0 at that initial position. There's our velocity vector. So our goal is to first find the position of the car when t equals 2. So to find the position of the car when t equals 2, what I'm going to do is say, first of all, to find the horizontal portion of this, x of 2 is going to equal x of 0 plus the integral from 0 to 2. The reason why I'm doing from 0 to 2 is because it's showing just the initial plus the displacement, which is going on right here. And the horizontal is 6t plus 1 dt. And I should be able to do this one by hand. So x of 0 is 1. And then the integral of that is going to be 3t squared plus t, going from 0 to 2, which gives us 1 plus 12 plus 2, which gives us 15. And I'm going to zoom in here. Now to find my vertical component, y of 2 is going to equal y of 0 plus the integral from 0 to 2 of 3t squared. So y of 0 is 2. The integral of 3t squared is t cubed, going from 0 to 2. So that equals 2 plus 8, which is 10. So the position at t equals 2 is going to be 15, comma 10. Now, this is where we get to see what we call the net change theorem. This net change theorem is something that I tried to get you guys to do a lot. A lot of people tend to view like integration and doing this as a differential equation style. This is not a vector value, right? Or this is just the position. We can come up with a vector value. We can come up with the overall vector value function. This is just the position at that moment. So this is going to be parentheses and not the angled brackets of a vector. So the angled brackets of the vector, our position vector, is going to be 3t squared plus t, comma t cubed. So that's actually what part C is asking. What is our position vector of the car? Let's go ahead and do that right now. Our position vector is going to be r of t is going to be our initial point. So we can consider our initial point as that initial, I kind of like to see this more as a point. That point plus the vector and this will be the integral of that vector, 6t plus 1, comma, 3t squared, dt. So that's going to be 1, 2, plus this vector of 3t squared plus t, comma, t cubed. So giving us 3t squared plus t plus 1, t cubed plus 2. The 1510 from before, it's a position. It's not an actual vector. So it's a position, so that means it needs to have the parentheses. Do we need to add the plus c? What's great about this is no, we don't, because this is really your plus c. So again, what I was talking about in terms of a lot of people wanted to do this as differential equation style, where you need to solve for all the individual c's. What's better about this mentality is if you take where you start. So if you take your start and then you add your change, then you get exactly what you want. So looking at it as, you know, your initial value plus your change is just so much better. And honestly, that's more of the AP style. That's what they're looking for. So it's hard to get students to change their own, like how you start with something. So it's something I tried to get going, but a lot of people ignored me, and I get that. Now you're paying the price of that. So shame on you. Just kidding, everybody. Is it acceptable to leave it as step 2? Probably. So find the total distance the car traveled on that interval. So if we want to find the total distance, once again, we're finding the integral of the magnitude. So we are given that velocity vector. And I'm going to keep this as the teal color. So the total distance is going to be the integral from 0 to 2. So the integral from 0 to 2. Once again, why that 0 is important is because we knew what happened starting at the very beginning, t equals 0. So this would be the integral of 6t plus 1 squared plus 3t squared dt, which we have 2 options. We can either try to do this manually, or we could just go to the calculator. And let me check and see if anything cool happens manually. This gives us 36t squared plus 12t plus 1 plus 9t to the 4th. I'm not seeing anything really cool happening on that one. So since I don't see anything cool happening, let's just go ahead and go to the calculator. So if you remember shift plus, integrating from 0 to 2, let's throw in the square root. Yes, it's probably a good idea. I'm gonna have to, now that I got distracted, let's try one more time. Shift plus, integral 0 to 2. And then here's where I need the square root. So the square root of, I'm just going to go ahead and put the initial just in case I made any mistake, which I don't think I did, but it's kind of like better practice. Better practice just to take what they give you and run with it, as opposed to doing too much math on your own, especially if you're using a calculator for it. So 3t squared, oops, and then dt. I get 16.4115, so about 16.412. The calculator, the way the calculator approaches this, I don't know if you've ever seen a TI-84, if you have one. This is Math 9. It's not magic, by the way. There is no such thing as magic when it comes to math. Math is beautiful. Math is art. So a lot, I just said, it's not magic. You know, a lot of joking aside, a lot of the early algebraists were considered to be witchcraft, great. a lot of the early algebraists were considered to be mathematical artists just because of how it all just goes together. You guys are cracking me up, by the way. I love this chat. So anyway, so how does it do it? This does it by numerical integration. What it's doing is it's plotting small values over and over again. Noun unit time, by the way. So it calculates small intervals and then calculates the value of the intervals. Basically, it's doing Riemann sums. Riemann sums with like predetermined t-values. So hopefully that answers your question before all the side topics of pretty much gold 4 class. So I love you guys and I do miss you guys. So problem number 3. I'm going to do this in a different color. I'm given the acceleration vector, I'm given the initial velocity vector, and then I'm given my initial position. This time I'm giving it as a vector. So let's go ahead and find the velocity and position vectors. Our velocity vector, so v of t, and this is supposed to be a bolded v, you just can't see it very well. Our v of t is going to be v of 0. And then that will be v of 0 plus the integral from 0 to, do I want to do it this way? Yep. Let's do 0 to t. This kind of uses the second fundamental theorem of calculus if we apply it in this direction. So we'll take the integral from 0 to t of, I'm going to now call this cosine. I need a dummy variable. Let's call it n. Cosine of n. 3 sine of n, probably shouldn't have used n because of the sine, but too late now, dn. So this gives us 0, -3 plus the integral of cosine is sine. So it'll be sine of t now, actually. Sine of n, -3 cosine of n. Going from 0 to t. So again, I'm going to leave it as 0, -3 plus the sine of t. And I'm just going to kind of join these together, sine of t minus 0. And then -3 cosine of t. And then this is where we have to be careful. It'll be minus, the cosine of 0 is 1, so minus -3. So put it all together, I will get the velocity vector sine of t, and then I will have -3 plus -3 cosine t plus 3, which is -3 cosine t. And that is my velocity vector. I'm going to scoot this over because, you know, par for the course. I really didn't give myself enough time or enough space to come up with the position vector. So let's go ahead and do our position vector. We're going to do something similar. R of 0 is -1, 0 plus the integral from 0 to t. And we'll use a dummy variable again. This time, let's use c. Oh, thank you. R of t. So let's, I'll go ahead and use, actually, let's use a as a dummy variable. No particular reason. So the integral of sine is negative cosine of a, and then the integral of -3. Actually, I shouldn't integrate just yet. That's what I get for insulting people indirectly. Sine of a, -3 cosine of a dt. Possibly. I'm just reading the group chat. So it's going to equal -1, 0 plus, and then this is where I get the negative cosine t.
Isn't it dA, not dt?
Thank you. Appreciate the correction on that one. Going from 0 to t. So -1, 0 plus negative cosine t minus -1. and then it'll be negative, I guess this is still an A right here. Then it'll be negative sine t minus 0. So altogether, very happily, this turns into negative cosine t. Then
Isn't it
sine
negative
t.
3 sine, negative 3 sine t?
Yeah. Pardon my epileptic notepad. I lost the negative 3. Thank you for that. All right. I think we're finally good. So now if I want to find the position at t equals 4, I really should have changed the spacing on this one. So to find R4, it's just going to be negative cosine of 4 and then negative 3 sine of 4. Question is this calculator or no? If this is calculator, let's go ahead and make sure that our calculator is in radian modes. I've been in pre-calc using this calculator a lot, so it was in degree. So I made sure I switched it. So what is the negative? So what is the negative? I want to negate cosine of 4. And I need to have a decimal point. So that's about 0.6. You're hearing happy kids in the background, which I'm glad they're happy at the moment. And then negative sine of 4.
Is this parentheses or is this a
It's a vector.
Is it supposed to be in parentheses or vector?
Actually, since it's a position, I mean, honestly, it's kind of both. Although that kind of extends to a good question. Since we could look at it as either a position vector or a position coordinate. So this is our position vector that is stemming from one common point. One of the things that we never really talked about when it comes to vectors is that with vectors, you can establish, like, a vector doesn't really necessarily have to have a starting point. If you look at what we did up here, we established what was going on with the vectors starting at a specific point, but we could have moved those vectors anywhere, and those vectors ended up still having the same value, because vectors just really imply what force is going on. One of the ways that I think about vectors sometimes is, imagine that you're in a boat, and the current in the water is a vector. The wind is another vector. That the current in the water and the wind, as those vectors are kind of like intersecting with each other, it's causing the boat to move in a certain direction. But they don't necessarily, like, those vectors for the wind and the current don't have like a single starting point. Where one of the things that we like to do is say, okay, what's the position of the boat? Let's kind of apply both vectors there at the same time to figure out what's going on in the end. So anyway, I got distracted, and going back to this, let's go ahead and put a decimal point, 0.75.
Isn't it negative 3 sine of 4? Not negative sine of 4.
Yes. That's what happens when I get distracted. 2.270.
I think that's the best notation, half parenthesis, half angled.
Oh, I love you guys. If you only knew what was going on in my mind right now, do you understand why I am just like mixing up all these different things? All right, anyway. Why do I add the values for R of 0 and then subtract them again? So the values for R of 0, so R of 0, let me do this in highlighted mode. R of 0 got built into this expression. Since R of 0 got built in that expression, this allows me to find the overall position no matter what. So kind of like answering what somebody's saying on the group chat, this right here, this R0 represents your plus C. So rather than looking at it as plus C and then solving for time and kind of going through all the differential equation work on those, let's just go ahead and say, I'm going to build that into the equation by saying what's my starting value and then what's the overall changing vector. So what's the starting vector, what's the changing vector? I'm not sure what analogy is being referenced, but okay. Anyway, moving on. Let's go to our last example of the entire notes for the year. So particles moving along the curve given by that position vector. Is a particle moving to the left or the right when, gotcha, when t equals 2. So, not you, your sister. Mary, shh. So if I have particles moving to the left or the right, because it's left or right, I need to know what's going on with that horizontal vector, not the vertical. So since I care about that, I know that if dx dt is greater than 0, then I'm going right. If I know dx dt is less than 0, I'm going left. So since this is my x of t, I'm going to look at, let's go ahead and put r prime of t up here. R prime of t is going to be 3t squared minus 12t, comma, negative 2t plus 8. So my x prime of t is it's positive 3t squared minus 12t. What is x prime of 2? X prime of 2 is negative, that's actually positive. So 12 minus 24, which is negative 12. So since x prime of 2 is less than 0, we are moving to the left. So how would the AP answer this if this was disable annotation? Thank you, guys. So no, that was not Beck that did that. That was somebody else. So anyway, how the AP look at this, I would say the answer is the particle is moving left. So the particle is moving left since x prime of 2, or I probably should say dx dt at x equals 2, or t equals 2, is less than 0. All right, what's the velocity of the particle at time 2? So r prime of t is going to be our velocity vector. Now, all of these should be bolded. It just takes too much time, in my opinion, but definitely important. So this is, we already found out that this one, the x is negative 12. And then the y, well, that's negative 2 times 2 plus 8. So that would be negative 12 comma 4 as a vector. At what point is the particle at rest? So the particle is at rest. Let's go ahead and write this. The particle is at rest. Is at rest when dx dt equals 0 and dy dt equals 0 at the same time. Do you always have to bold it when you write? You're supposed to, but most of us will not, just going in with the knowledge of, hey, we know that we're working with vectors and they should be bolded. If you have the technology to show that it's bolded, great. Sometimes you might see it written in this way to kind of show that that R is bolded as R of t. Can you put an arrow on the top to show the vector? In physics, I know they do that a lot. What does the arrow truly represent? Or it's kind of like called a hat. So when you do that, there's a lot of relationships to unit vectors. we haven't discussed it, but that's something that you'll discuss in multivariable. When I have taught multivariable in the past, I've kind of defaulted to using the hat just to kind of represent what's going on. Question, we'll accept a lot of varieties of notation. So anyway, going back to this question, when does dx dt equal 0 and dy dt equal 0? So dx dt equals 0 when 3t squared minus 12t equals 0. I know a lot of us can factor this without writing it out. Let me zoom in so I'm not writing quite so messily. So this happens at t equals 0 and t equals 4. dy dt equals 0 when negative 2t plus 8 equals 0 or t equals 4. So particles at rest only when t equals 4. All of my justifications should be built into this, that I've established dx dt equals 0, dy dt equals 0, and at that point. So now that's at the time. Let me go back to the question. At what point or points is the particle at rest? So what is R of 4? R of 4, going back to my question, what is 4 cubed? 64. So 64 minus 6 times 16. Calculator, because I can't think at the moment. I guess that's 96. 64 minus 96 is negative 32. Let's just go ahead and kind of finish writing that. And then it would be negative 16 plus 8 times 4 is just 32. So that gives us the, at the point, since they want the point, negative 32, comma 16. Remember that point is kind of built into both. Like I could write it as a vector, which is not necessarily a vector. They want this as a specific point. And very last thing, what is our total distance traveled on the interval from 0 to 4? That would be the integral from 0 to 4. And just remember, this is x prime squared plus y prime squared. So x prime, I'm not given. So I found it though, 3t squared minus 12t squared plus negative 2t plus 8 squared dt. And I'm going to go ahead and do this in the calculator because I feel like I've earned the right to be lazy. Although I'm not sure if this one can be easily done or not. So integral from 0 to 4, and then square root. Three t squared minus 12t squared, and then plus negative 2t plus 8. And I get that nasty looking thing. So let's go ahead and throw it a decimal point somewhere just so that we can get value. 37.581. So total distance 37.5801 or 0.580. And everybody pat yourselves on the back because we are done with all of the new learning for this year. Yay!